بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 4.2 linear programming, and we will talk about graphical method in this section. So linear programming is a technique that can be used to solve problems such as maximize or minimize an objective function. So there is a function which we need to maximize or minimize, and this function we call it objective function. And this function will be subject to uh, constraints, some constraints. So what are the constraints? This is the limitations we put on the variables, and usually they are in the form of some inequalities. So this problem, when the objective function is linear function, we call it LP problem or linear programming problem. Well, to solve LP problem by graphing, we will talk here in this section about systems of linear inequalities in two variables. The solution is determined by a region. Okay, any point in this region is a possible solution. This region is called feasible region, and any point in this region is called feasible solution of the system. Well, here we will deal with closed and bounded regions, and also with regions that are not closed and not bounded. So if the feasible region is closed and bounded, then the objective function will have a maximum and a minimum value. While if the feasible region, is not closed and not bounded, not closed and bounded, so the objective may have maximum only or minimum only, or sometimes no solutions, as we shall see. If a linear programming problem has a solution, then this is important, then the maximum or the minimum value of an objective function occurs at a corner point of the feasible region. So the solutions, the maximum or the minimum, occurs always at the corner points. If the objective function has an optimal value, maximum or minimum, at two corners, then it also has the optimal value at any point on the line connecting these 2 points. Look here to the procedure of how to solve the linear programming problem. So to find the optimal value of a function subject to constraints. So a question, an example, find the maximum and minimum values of. So this function is the objective function. You can see that it's a linear function because x has power 1 and y has power 1, subject to constraints. So these are the constraints, okay, 2, 3, 4 constraints. So how to find the maximum or the minimum of this objective function? We first write the objective function and the constraints, and then we graph the feasible region. Okay, we graph the solution of the constraint system. Okay, so this is, for example, the feasible region. If we find in this case, in this example, that the feasible region is closed and bounded. Okay, the region, as you can see, is closed and bounded. If the region is not closed and bounded, then uh, we it may have one a maximum or a minimum, or no solution. Now we find how to find the maximum or minimum or both. We find the corner points. So for example, here I have 1, 2, 3, 4 corner points. So these are the corner points 0, 5, 0, 0, 7, 0. And when we find the intersection point between these two lines, it would be 6 and 2. And now we evaluate the objective function at each corner of the feasible region. So these are the 4 corners. We evaluate C at each point. X is 0, Y is 0, and we find the value of C. And the maximum value of C is 18. So we say that the maximum value is 18, and the function is maximized at x equals 6 and y equals 2. The function is minimized at x equals 0 and y 0 because the minimum value of C is 0. So at the corner points, we will find the minimum value and the maximum value, and where is each one of them occur. Let us see this example. Minimize the objective function. So the question is minimize. Find the minimum. This is a linear function. All right. If you solve this function for y, for example, so y would be take 3x to the other side. So it's 3x plus f. So we need to find what is the minimum f. Okay, maximize. What is the maximum f? F is the y-intercept. If you put x0, f here is the y-intercept. And the slope of this line, the objective function is linear function, is -3. So we have these constraints. So we start by graphing the region determined by these constraints. Well, this is the region, okay. And if we choose a point, for example, 4, 6, in this region, and replace x by 4 and y by 6, we will get 12 plus 6, 18. So the y-intercept of the line that passes by 4 and 6 with slope -3 is 18, the y-intercept. If you go up, you will reach the y-axis at the point 18 because the y-intercept is 18. Now, is 18 the maximum possible y-intercept, or maybe there are more? Of course, we know now that the maximum will happen at the corner points. These are the 4 corner points, 1, 2, 3, 4. So we can make a table, corner point. So we have 0, 0. We have 0, 10, 10, 8. And we have 14, 0. And at each one of them, we find the value of f, or the y-intercept. So at 0, 0, 0 plus 0, f would be 0. At 0, 10, x is 0, y is 10, so f would be 10. At 10, 8, 30 plus 8, that's 38. At 14, 0, 3 times 14 is 42 plus 0. So we can find that the maximum value of f is 42, and it happens when x is 14 and y is 0. And this is the line. Notice that all the lines would be parallel because they have the same slope, -3. Only f is different, the y-intercept. So the line that passes by the point 14, 0 will have a y-intercept of 42. We have this line which passes by 20, 0. A y-intercept is 60, but this line, this point 20, 0 is not a point here in this region. So we searching for the solution in this region, okay, the feasible region. So the answer, the maximum is 42, and it happens at when x is 14 and y is 0. So maximum f is 42 at x equals 14 and y equals 0. Find the maximum and minimum values of the objective function on the shaded region in this figure. So this is the shaded region. It's closed and bounded. So there will be a maximum and minimum. I need to find the corner points. This corner point is 0, 4. So corner point 0, 4. This is 0, 0, 3, 2 is the intersection point. And this point is 2, 0. 6, 0 is not a corner point of the feasible region. So now I have 4 corner points, and I put them where? In f, the function, the objective function. So 4 times 0 plus 3 times 4, that's 12. 4 times 0 plus 3 times 0 is 0. 4 times 3, 12, plus 2 times 3, 6, that's 18. And 4 times 2 is 8, plus 0, so this is 8. So the maximum value, of f is 18 at x equals 3 and y equals 2. And the minimum value of f is 0 at x equals 0 and y equals 0. So this is the answer of this question. We have found the maximum value of f and also the minimum value subject to these constraints. Find the maximum and minimum value, if they exist, of this objective function c equals x plus y subject to these constraints. So what to do? First, we graph the feasible region. Okay, so to graph the first inequality, I start by graphing the line 3x plus 2y equals 12. And to graph the line, I need 2 points. So I choose x0, 2y 12, so y is 6. I choose y0, 3x is 12, so x is 4. And let me start by sketching. So this is 0, 6, and this is 4, 0, and this is the graph of the line. Okay, this is the line, 3x plus 2y equals 12. Now if I choose 0, 0, then 0 plus 0 is greater than or equal to 12. This is not correct. So 0, 0 is not in the region. So this is the region here. Okay, x is greater than 0, y is greater than 0, so we are in the first quadrant. And x plus 3y equals 11. This is the second line we need to graph. If x is 0, y is 11 over 3, or 3.6 approximately, 11 over 3, 3.6. 6 or 3.7. Okay, 7 is okay because after 6 I have 7. And if y is 0, then x is 11. So this is 4, this is 11. So the point 11, 0. 0 and 3.7, 1, 2, 3. So it's about here. So now I connect these points, and this is the line x plus 3y equals 11. And let us check the point 0, 0 in the inequality. 0 plus 0 is greater than or equal to 11. This is not correct. So the point 0, 0 is not in the region. So here is the region. Now don't forget that x is greater than 0 and y is greater than 0. So this would be, this is the region. Okay, this is the region. We notice that this region is not bounded. Okay, it is not closed. The corner points, where are the corner points? I have this point is a corner point, this point is a corner point, this point is a corner point, and that's it. So here, this region satisfies all the, the constraints. So this is the feasible region. If this function has a maximum or a minimum, it would be at one of these corner points. Of course, this function has no maximum because it could have, C could be maximized here at points different than the corner points. Okay, because if you go up, you can find maximum values for C. So corner points are, this point is 0, 6, and this point here is 11, 0, and this point is the intersection point between the two lines. So let me solve, let me solve the two lines together. So 3x plus 2y equals 12, and x plus 3y equals 11. Well, I will multiply the second equation by negative 3. So I will have 3x plus 2y equals 12. Multiply the second by negative 3. So negative 3x, negative 9y, negative 33. Add negative 7y equals negative 33 plus 12. That's negative 21. So y is negative 21 over negative 7, or 3. Now if y is 3, then x plus 3 times 3, 9 equals 11. And then x is 11 minus 9, or 2. So the point is 2 and 3, okay, which is possible. But of course, my graph is not 100% accurate. So the point is 2 and 3. These are the three corner points, and let us put it at the function c. C is x plus y, so 0 plus 6 is 6, 11 plus 0 is 11, 2 plus 3 is 5. So I can say that C has no maximum, no maximum value for C, but minimum value of C is 5 at x equals 2 and y equals 3. Why there is no maximum? Because, for example, this point here, 20, 0, is a point on the region, isn't it? On the feasible region, not 20, 0. Take 20, 20 is a point on the region, and 20 plus 20, 20 plus 20 will give you 40. So C can go to infinity, okay? So because it's unbounded, there is no maximum value for C. But the minimum value is 5. And if you replace C, if you choose any point in this region, you will never find the a value of C less than 5. The minimum value of C is 5. Find the maximum and minimum values, if they exist, of this objective function subject to these constraints. So we start by graphing the region, the feasible region. First, we graph the line x plus 2y equals 12. If x is 0, y is 6. If y is 0, x is 12. The other line, 3x plus 4y equals 230. If y is 0, x is 10. And if x is 0, 30 over 4 is 7.5. Let us sketch the graph of this region. Now, 0, 7.5, and 10 and 0. So this is the first line, and 12, 0, 0, 6. Okay, and this x is greater than 0, and y is greater than 2. So this is the line y equals to 2. So y is greater than 2, and x is greater than 0. So where is the region? This is the region. It's again unbounded and not closed. It's open. And this point is a corner point. This point is a corner point. This point is a corner point. And this is the region. It goes to infinity, okay? To infinity. This is the feasible region. All right. So also there is no maximum. There is no maximum in this case. I did not check the 0, 0. So let me do it. If I check 0, 0 in the first inequality, 0 plus 0 is greater than or equal to 12. That's not correct. And 0 plus 0 is greater than 30. That's not correct. Oh, good. So our graph is correct. This is just by luck, because I have to check 0, 0 first before I determine the feasible region. So everything is okay. There is no maximum value, but the minimum, to find the minimum, we need to determine the corner points. So this corner point is 0, 7.5. Now this corner point, y is 2. Okay, I can see that it's 10 and 2, but I need to find it to make sure. So let me write the equations. Well, this line is the line 3x plus 4y equals 30, and this line is x plus 2y equals 12. So this point is the intersection point between the line x plus 2y equals 12 and the line y equals to 2. So x plus 2y equals to 12 and y equals to 2. So I just put y here. So I have x plus 4 equals to 12, or x is 8. So x is not 10. Okay, so my my graph is not accurate as usual. So 8 and 2. So this point has coordinates 8 and 2. This point, okay, 8 and 2. And now to find the coordinates of this point, it is the intersection point between the two lines. So I have 3x plus 4y equals 30 and x plus 2y equals 12. I will multiply the second equation by -3 to use the elimination method. And now -2y is -6, so y is 3. If y is 3, then x plus 6 is 12. So x is 6 and the point is 6, 3. So this point is 6, 3, which is okay, possible. So these are the 3 corner points. We do what? We substitute in g. G is 3x plus 4y. So 3 times 0 plus 4 times 7.5. 4 times 7.5 is 30. 8 times 3, 3 times 8, 24. 2 times 4 is 8. So 24 plus 8 is 32. And 3 times 6 is 18. Plus 3 times 4, 12. That's 30. So there is no maximum. We know that there is no maximum because G could be maximized more than 32 at a lot of points here, but there is a minimum. So where is the minimum? The minimum is at the point 0.7.5 and the point 6.3, which is this point. This is 6.3. So this line that passes by 7.5 and 6.3, this line here, any point on this line will minimize the function g. So minimum value of g is 30 on the line connecting 0.7.5 and 6.3. So this is what he meant in the beginning of the section when he said here, if two corners give the optimal value, then all points on the boundary line joining these two corners also optimize the function. That's the end of this section. Thank you very much. Hope it's enjoyable for you.